Hi everyone, my name is Aditya K. Kamath. Today I'm presenting MC2, lazy memcopy at the memory controller. Prior work has shown that memory movement consumes a high amount of overhead across many processes. A 2015 paper profiled the behavior of applications in Google's data centers and found that up to 7% of all CPU cycles were consumed by memory movement. In addition, RPC calls and protobuf also had high copy overheads. Another paper profiling Meta's most popular microservices in 2020 saw similar trends with copy overheads of up to 14%. We ourselves conducted a study on several operations across different application domains that exhibited a high copy overhead. We plotted flame graphs showing the amount of time spent in various functions of these operations, including memory copy times. The top two graphs depict writes and insertions for an OLTP and NoSQL database respectively, while the bottom left graph shows operating system copy on write faults, and the bottom right graph shows common protobuf operations. The bars highlighted in purple show the time spent copying, which can be up to 68% for these operations. Our insights from looking at these applications are that these applications typically use MemCopy to fill temporary buffers. This can lead to excessive or redundant copying. When copying happens in the critical path of application processing, it becomes difficult for the CPU to hide its overhead, leading to killer microseconds of copy execution. To see how copies are used in modern applications, let's take a look at a typical use case. Specifically, read copy updates in multi-version concurrency control databases. Multi-version concurrency control, or MVCC databases, copy rows or tuples being modified to local buffers to preserve isolation guarantees. In this example, we see two threads performing transactions on the database concurrently, with one writer and one reader. Before performing the modifications, the writer creates a copy of the row that it wishes to modify. The writer then performs its required modifications to its local copy. This allows the reader to read the unmodified data from the original database and avoid inconsistencies in operations. When the writer commits the transaction, it merges its row back into the main database. The entire row may not end up modified, in which case the writer copied more data than it actually needed to. In addition, there's potential for copy overheads to be hidden in the background while other database operations are ongoing. Currently, applications make use of what we refer to as eager copying, where a copy operation causes data to be moved. Then, on access, the required data is obtained. For the applications we previously saw, we find that this is not the best approach for data movement. We instead propose performing data movement lazily. On a copy operation, we don't actually do anything. When the data is finally accessed, we reroute the request to the appropriate location, performing the data copy in place. This method only copies data that is accessed from memory, and furthermore, this allows the hardware prefetcher to trigger copies before data is accessed to hide the copy latencies. To support this operation, we propose MC2, performing lazy memcopy at the memory controller. We find that the memory controller is the ideal place to handle this, as all memory access must pass through it, and it frees up responsibilities from the CPU, providing opportunities for copy hiding. This system consists of three main components: hardware modifications to the memory controller, new instructions, and a software wrapper. We'll now look at each of these in depth. We add a copy tracking table, or CTT, which tracks all the prospective copies. Each entry in this table contains a 52-bit destination address, a 52-bit source address, and a 21-bit size of executed copies, along with an active bit to check whether the entry is in use. We use 52-bit for addresses since this is typically the size of physical addresses in systems today. The 21-bit size allows each entry to track a prospective copy of up to 2 MB in size, or the size of a large page. The entries in the CTT are kept coherent across memory controllers, and the CTT is looked up in parallel with memory access, hiding its access latency in the critical path. We also maintain a bounce pending queue that temporarily holds writes to source buffers for consistency. The importance of the bounce pending queue is explained in detail in our paper. We provide two new instructions to take advantage of MC2. The first is MC lazy, which initiates the lazy memcopy operation. It accepts three registers: the destination virtual address, the source virtual address, and its copy size. The second instruction is MC free, which is a hint that informs the system that the address provided is no longer in use and does not need to be tracked anymore. MC lazy has a few alignment restrictions to simplify hardware. We provide software wrappers that hide these low-level constraints from the programmer. The first constraint is that the destination buffer address must be cache line aligned. This is because memory accesses occur at a cache line granularity, and lazy copies on partial cache lines would make the hardware overly complex. The second restriction is that the copy size must be a multiple of the cache line size for the same reason of avoiding partial cache line copies. And the final restriction is that the destination and source buffers must be contiguous in physical memory. For user space applications, this means that they must each lie within a single page. For copies spanning multiple pages, MC-lazy should be called on each page. As previously mentioned, we provide a C wrapper around MC-lazy that exposes a lazy memcopy with identical semantics to libc memcopy for programmer convenience. Full details on how this is done is mentioned in the paper. We'll now look at how the lazy copy operation is performed and what happens on memory access. Let's assume that the CPU core executes an MC-lazy operation on a destination and source cache line. The CPU creates a packet for this operation and sends it towards the caches. At the caches, the operation triggers an effect where the destination cache line is invalidated and the source cache line is written back. This ensures that further access to the destination reach the memory and that the memory has up-to-date values of the source that were supposed to be copied to the destination. The packet is then broadcasted to all the memory controllers where the operation is added to the copy tracking table. We'll now see how reads to the destination buffer are impacted by this operation. When the CPU reads the destination, we need to obtain the data from the source instead, since the data wasn't actually copied. The access proceeds as normal initially, and at the memory controller, we consult the CTT and realize that this was the destination of a prospective copy. This causes the request to be bounced to the memory controller containing the source cache line. The source cache line is read from memory and sent to the CPU core as if it was read from the destination memory location. Reads to the destination incur an additional latency due to the CTT lookup and bounce operations. In our paper, we also detail out how reads to the source and writes to the source and destination buffer are performed. We now have a few questions that we wish to quantify in our evaluation. Namely, how much lower is MC-square's copy overhead? What impact does it have on access times? And what benefit could MC-square provide real workloads? In our paper, we also answer a few more questions that we won't be able to cover here. To answer these questions, we make use of Gem5, a cycle-level CPU simulator. Our configuration models a scaled-down server node with 8 CPUs. Wherever possible, we compare against Zio, an OS-based copy-on-access mechanism that makes use of OS-managed page tables to align copies. Zio is essentially the OS-based approach to lazy copying, which requires expensive page table management operations when accessing lazily copied pages, giving it high access penalties. To evaluate the latency of copying, we performed an experiment where different sized source buffers were copied to destination buffers. Note the y-axis is in log scale. We evaluate against memcopy in two scenarios. The first is where none of the data is cached, referred to as just memcopy, whereas the second is where the source and destination buffers have just been accessed before copy, allowing them to be cached. These are essentially the best and worst case performance for memcopy, and copies with high overheads due to high memory access latencies behave closer to the uncached memcopy performance. MC-square provides speedups for copies at and above 1 KB, performing similar to copying cached data at 64 KB and above, and is up to 11 times faster than uncached memcopy. Since Zio relies on page table manipulation, it only ran for copies at and above a 16 KB size. It has a high initial overhead due to page table manipulation and TLB shootdowns. Below 256 KB, MC-square outperforms Zio, and above this, Zio outperforms MC-square as MC-square relies on cache line flushing, which has its own overhead. Despite this, we shall see how MC-square still provides benefits at these sizes. To analyze the impact of lazily copying on access latencies, we ran a micro benchmark where a 4 MB source buffer is copied to a destination buffer. The destination is then accessed sequentially, and because the buffer exceeds the LLC size, none of the data is cached. We intentionally misaligned the source and destination, as in the applications we examined, the source and destination buffers are typically not cache line aligned. For our system, this causes additional access latencies to fetch data, the full details of which are in our paper. The runtime of each system is normalized to the time taken by memcopy, with higher meaning slower. We analyze the runtime when different percentages of the 4 MB buffer are accessed. As we previously saw, Zio outperforms MC-square when the dataset isn't accessed at all. However, once we start accessing the destination, Zio starts seeing page faults, which triggers copies. When more than 25% of the dataset is accessed, it performs worse than memcopy, whereas MC-squared is able to retain low access penalties throughout. Surprisingly, even when the entire dataset is accessed, MC-square outperforms memcopy. This is because the cache prefetcher hides some of the extra access latencies. And when we turn off the prefetcher, we see that it slows down compared to memcopy, showing the impact of copy latency hiding. When the source and destination buffer are aligned, we see even better performance. Moving on to the performance of applications with MC², we see that many database transactions involve updating only small portions of a tuple. For example, in TPCC, decrementing the quantity of stock of an item being sold in a store may only update 1 to 2% of the total tuple size. As we previously saw, this leads to excessive data being copied for the read-copy update performed by MVCC databases. With MC², we can pay only the copy overhead for the portion of the tuple updated. And to evaluate this, we enhanced the Cicada database with the MC² and performed repeated operations on a table with 8 KB sized rows, modifying different factions of the tuple and measuring throughput. These operations are split 50-50 between reads and updates, which are typical of write-intensive database workloads. We used 8 threads saturating the cores in our system. Here, MC² is able to provide up to 78% higher throughput since it reduces the memory bandwidth consumed for smaller update fractions. We also analyze MC² with a protobuf workload provided in Google's Fleet Bench benchmark suite. Fleet Bench contains workloads dedicated to common hot library functions constructed using traces from production servers. We find that MC² has 43% lower runtime compared to memcopy. Zio is unable to generate any performance benefit since all the copies in this benchmark were smaller than the 4 KB page size it requires to light copies. We also replicated an experiment from the Zio paper where MongoDB insertions are performed using 100 KB fields and 10 fields per insertion. Here, MC² provides an average 15% lower latency for insertion, while Zio slows down by 9%. This is because the copied data is later accessed, triggering page faults for Zio, which MC² avoids. To summarize, we introduce MC², a novel lazy copy mechanism at the memory controller, which provides up to 11x faster copying than standard memcopy. It provides benefits across workloads such as protobuf, MongoDB, and MVCC databases, and our code is completely open source on GitHub. Thank you for attending this talk.